Hello, it's Keith from Kinvert, and we're going to be going over a real-world use of an exponential function. We're just going to be kind of evaluating the value of the function. So basically, let's say there's like a nature preserve, and they put 75 deer in there, and they're estimating that the growth rate of the deer is going to be 0.8 as far as the population. Right, and then they want to know, like, in 1 year, how many deer they're going to be approximately. In 2 years and 5 years, approximately how many deer are there going to be. And they estimate that the equation is going to take this form, and they'll adjust later and maybe count the deer later and then adjust their growth rate and stuff like this. But this is the prediction, and this is what they're basing their estimate of why they need 75 deer, blah, 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 right? They want to hit some population numbers, whatever. So, we have a function of time. So n is like, number is a function of time, and this is in years, right? And then we've got n sub 0, like, sub 0. This isn't this is number initial, like time 0 or whatever. So this is the initial deer population. E is literally just E, right? 2.718 approximately. It's a bigger number than that, more decimal places. R is the growth rate, and t is the time. So I want you to sit here and try to figure out how you would construct this function on your own. So pause the video. I'm going to start giving the answer in 3, 2, 1. All right, so what we're going to do is say n of t. I'll just write it up here with the info that we have. We've got n of t, so this is a function of time, is n0, which is 75, that's the initial number of deer, times e to the r, so we have 0.8 times t, which is our unknown. It is our independent variable here. That is what the function is following. So that's basically the function. And now we are going to try to calculate out what we estimate the population to be at these times. So I'm going to start constructing this in my super duper calculator of power, and why am I doing that? 0.8 times t, and I'm ready to roll. I hope I have it right. I guess we'll find out later. So yeah, I don't even know how to check these answers really, but let's go with it. All right, so we've got this. And here comes your answer soon. I want you to try to figure out on your own what these answers are going to be. And pause the video now. You can hit the K key. I'm going to start giving the answer in 3, 2, 1. All right, so we're going to start going over this. We've got, for the first one, n of 1 is 75 e to the 0.8 times 1, and go ahead and calculate that out if you can before me. Again, it's the K key, and so what I'm getting for this is 166.9. That poor 0.9 of a deer. I feel bad for that little fella. So this ends up being 166.9. I suppose that you would round this up to 167. I'm not a conservationist, so I'm not sure. So that is the estimated number, 167 deer. How wonderful, right? Now let's try the same thing for 2 years. N of 2 is 75. I'm not going to bother to write out the third one here. Hopefully you are getting the picture by now. This is multiplied by 2. And let's grab this back and evaluate that. Holy cow, those deer got pretty busy there, and there's already 371 of them. So we've got 371 deer. That is a lot of eaten grass. So we've got 371 by this time. And I will have you go ahead and calculate the 5-year. Holy cow. I'm thinking this is not very realistic. But what I came up with here is 4,095 deer conquering the world. How can you handle such an onslaught of deer? There's nothing you can do. So that's what this model is predicting. Hopefully the conservationist people would be like, hey, is that a realistic number? Because maybe we need to do the whole, I don't know why she swallowed the fly, bring in some wolves, they eat up some of those deer, but then the wolves then you get all these population things doing all this. But anyway, that's what this came up with. I called this a real world example, but that could be a bigger problem than global warming there. That I don't even know how you deal with that. But anyway, this is an example of exponential growth. We're applying this to deer in a conservation area, and they conquer that and move on to other domains, I guess. They go into space with that many deer. But we just literally built out the function. We need to know what each of these variables means, how we're going to model this, right? But it fell together pretty quick when you know the growth rate and you know the time. If you were solving for something, it might be a little tougher. Like what would have been a little more interesting would be for us to sit there and kind of estimate the deer population so that we don't have some sort of Terminator deer future where we're saying, hey, they're going to start off like this and kind of do this, and then you try to calculate out that growth rate and get an estimate for that. That might be a little more interesting, but then you're getting into regression or whatever you're getting into to actually fit that data, and that can actually kind of be done a little bit with machine learning. I don't think I'm going to go that far in this class, but maybe I'll have some like advanced options later. Anyway, that is how you can kind of model population. We're going to go over some more examples in the future of how to apply exponential functions like this. This is Keith from Kinvert. This is part of our online course for pre-calculus and algebra. There's an actual online course for this, so this will be on YouTube, but this is tied into more comprehensive curriculum that you can find in the link below. And yeah, please like and please subscribe. I've got like 200 subscribers. It's pretty lonely here. Only 2 people watch my videos, so thank you for your contribution there and being one of my 2 viewers. And anyway, I will see you guys in the next one. Bye-bye.